The Canadian Institute for Advanced Research brings together top researchers around the world to work in global networks whose focus is to answer big questions of importance to the world. One of CIFAR's programs is called the Quantum Materials Program. So quantum materials are the frontier of material science. Materials are at the basis of our technological world, and we're interested in exploring the new and exotic properties at that frontier. For example, quantum materials might be a good example is superconductors. Superconductivity is already used today mainly to make powerful electromagnets that are used in magnetic resonance imaging. But if we could make superconductors work at room temperature, then we'd have a major technological revolution. In the Quantum Materials Program, our mission is to understand how electrons behave, how they work in certain materials. To do that, we have three different kinds of experts. We have theorists, like Steve Kivelson at Stanford. We have materials experts, like the group of Bonn at the University of British Columbia in Vancouver, who make materials, synthesize the actual materials. And we have experimentalists. In 2007, we made a great discovery. We got samples from UBC, the group we'd been working with for 20 years as part of the CIFAR program, and performed measurements in Toulouse at high magnetic fields and observed what we call quantum oscillations. It showed us that we were not thinking in the right way about how electrons behave. And so now the field has really been transformed by that discovery.
What was so surprising about it was that people expected that in that range of the phase diagram, if you suppressed superconductivity, the material would be more or less insulating. The appearance of quantum oscillations is a sure sign that they're actually metals, not insulators. Our role in that was that to see quantum oscillations requires ultra-high purity crystals. And that came together with very high magnetic field measurements and then Louis Taillefer's group's expertise in quantum oscillations in other materials at Sherbrooke.
The role of a theorist like Steve Kivelson has been to guide us into where to look. The theorists are very effective in providing us guides, ideas, making predictions that we can test as experimentalists.
One of the key questions that many people addressed was, how does the system evolve as a function of doping from the undoped antiferromagnetic insulating state to the non-magnetic high-temperature superconducting phase? My collaborator Vic Emery and I thought a lot about this and addressed this by systematically looking at the solutions of simple models of doped antiferromagnets, and we came to the conclusion that the transition was first order, that the destruction of the antiferromagnetic insulating state could not occur smoothly and homogeneously in the system, but rather it occurred through some form of phase separation, which produces an intrinsically spatially varying inhomogeneous state and various forms of charge-ordered state as the low-energy consequences of that.
It turns out that the discovery led us pretty quickly to a new discovery, fundamental one, that in addition to superconductivity as the main property of these materials, there's another property, another phase of electronic matter sort of competing with it. And that's the key now to understanding how these materials function.
One of the key positive features of the CIFAR program in quantum materials is that the students have their own network within that quantum materials program. They run their own workshops, and they're actually highly mobile within the network.
So there are postdocs coming in from other labs, other program members sometimes, that are very motivated by what they do and transfer this motivation to us. So we have access to a variety of experts right here in the lab. So some people that I work with every day have made fantastic discoveries, and I get to be a part of this because they're here.
Well, CIFAR has had a big impact. It allows our researchers, our top researchers, established researchers, to directly connect to the state-of-the-art research being carried out in their fields.
CIFAR actually influenced a lot my work because, in a sense, my interaction with members of the program, I'm sharing a lot of my samples, but there's the feedback on my own research is important too. It's the key actually.
CIFAR has played a key role in bringing together these different experts from around the world to focus in a sustained way on answering these big questions that have the potential to transform our world.